We are given this function, capital F of x, that is uniquely defined. It's defined as a definite integral. Now, the great Sal Khan has an excellent video on this. What else is new? Everything he does, in my opinion, is excellent. But basically, this is an area function under this curve, 1 over 3t squared, and the area is going to depend on the value of x. So here we're going to start at 2, and we're going to look at the area under this curve depending on what this x value is. So this x value is going to vary, and if it moves to the right, you're going to have more of an area, and if it moves to the left, you're going to have less of an area. Next, we are asked to find capital F of x and capital F prime of x, and then evaluate the functions by plugging in 2. So in this first part, folks, we are not allowed to plug in x here. This is not a derivative of an integral. In part C, we're going to be able to do that. So for this initial part, part A, in order to find capital F of x, we're just going to follow our instructions here. So the first thing we're going to do is we're going to take the antiderivative of this. We're going to pull out the 1/3, and we're going to have the integral of t raised to the negative 2 power dt. We're going to add 1 to that exponent and divide by the new and improved exponent, which would be -1, which is the same thing as multiplying by -1. And if we were to go ahead and check and take the derivative of this, we would see that the -1 would come out front, making that positive, and that would reduce by 1, giving us -2 as the exponent. Now there's no plus c here because this is a definite integral, but let's go ahead and first plug in x. So if we plug in x, we are going to get 1/3 out front, and we're going to have minus x to the negative first power, and then we're going to have a minus here, and then we're going to plug in 2, and we're going to have -2 to the negative first power. All right, when we evaluate this, we're going to have 1/3 out front, and this is going to be times minus 1 over x plus 1 over 2. And when we distribute that 1/3, we're going to have -1 over 3x plus 1 over 6 as our final answer. Okay, so to complete part B, to do capital F of 2, we would just plug in 2 into capital F of x, and we would get -1 over 6 plus 1 over 6 equals 0. Okay, let's now move to part B, where we're asked to find f prime of x. Okay, to get f prime of x, here's capital F of x. Basically, we're going to take the derivative of both sides. So on the left, we're just going to apply the f prime, but here we're going to apply the derivative operator to the right side. So basically, we took the derivative of the left, the derivative of the right. So if we apply the power rule, we're going to have 1 positive 1/3 x to the -2, and we're going to bring the x squared in the denominator, and this is our final answer. Now, folks, here's the fundamental theorem of calculus at work. If you are going to take the derivative of an integral, so if we went ahead and we applied the derivative operator to both sides, and we had f prime, if we did the same thing over here, the fact that we are taking the derivative of an integral lets us take this x, as long as this is a constant, and plug it in for t, and the answer would be 1 over 3x squared. And don't forget, for the chain rule, we have to take the derivative of that x, which would be dx dx, or 1. So folks, the point is that we get the same answer if we do it in 2 steps. First, find capital F of x based on these instructions, and then take the derivative of that right over here, 1 over 3x squared, versus using the fundamental theorem of calculus where we're taking the derivative of an integral, and that lets us plug in the x, take the derivative of that, and we get the same exact answer. Next, we are asked to use the fundamental theorem of calculus to find the definite integral from 1 to x of this function of t dt. So folks, when you see the words fundamental theorem of calculus, you're tempted to go ahead and plug that x directly in for t, as was done here. But that is incorrect. I leave this up here to show an example of what you can't do, because there's no derivative operator in front of that integral. So what we need to do is follow these instructions. So let's go ahead and do that. Let's take the antiderivative of this and then plug in the 1 in the x. So the antiderivative of t squared minus 4t plus 1 is going to be t cubed over 3 minus 4t squared divided by 2 plus t. Simplifying, we're going to have t cubed over 3 minus 2t squared plus t. So now we're going to evaluate that by plugging in the 1 and the x. When we plug in the x, we're going to have x cubed over 3 minus 2x squared plus x. And now we're going to plug in the 1. When we plug in 1, we're going to have minus 1/3 minus 2 plus 1. And when we simplify this out, folks, this is going to end up being x cubed over 3 minus 2x squared plus x plus 2/3. In the next part of this exercise, they want us to take the derivative of our answer. So here's our answer here. We took the antiderivative, we plugged in 1 in x, and we have this function here. Now they want us to take the derivative of that. So f prime of x would be, using the power rule, it would be x squared minus 4x plus 1. So folks, here's the lesson. If your goal all along is to take the derivative of this, then all we have to do is apply the derivative operator in front of the integral. When we have that scenario, and only when we have that scenario, we are allowed to plug in as shown here. We're allowed to take this, as long as that's a constant. Is that a 2 or a 1? I can't remember. It's a 1. As long as that's a constant, we're allowed to take that x and plug it in if our goal is f prime of x, and we would end up with x squared minus 4x plus 1. And that maneuver, that, don't forget, you have to take the derivative of that. In this case, it's just 1, and multiply that for the chain rule. So the essence is that if your goal is to get f prime, take the derivative of both sides. If you have the derivative operator in front of the integral, then and only then are you allowed to plug in. And this is an easier alternative to following the directions here, taking the antiderivative, plugging in these two values, and then taking the derivative of that. Rather than go through that, it's much easier to go ahead and plug in, as shown here.